Okay. Thanks, guys. So look, once you've got the hang of this Velcro thing, you sort of think, wow, we could really do some great stuff with this. Why don't we scale it up? Let's have massive, giant Velcro. Well, look, for the first time ever in the Royal Institution, we've got giant Velcro. And we thought, well, you know, let's try it out. So I need 4 volunteers to help me with this. Yes, OK, brilliant. What about you? Yes. And you there. Yeah, you. And over there, yeah, you. Yeah. This could be a new step forward in technology. So what I'm going to try and do is I'm going to try out this giant Velcro. So it's a bit heavy, and there's 2 handles here. You think you two could manage that? Is that all right? Is that not too heavy? And you guys, you've got actually the heavier bit. Sorry about that. Are you all right there? Fantastic. OK, right. Now look, we've exactly scaled Velcro up proportionally. So these 2 bits and the thickness and the length, everything's the same. Let's see if it works. OK, off you go, guys. In the middle. Yes. Now, that should have stuck, so we'll test. Pull it apart slowly first, just to see. Yes. OK, well, that sort of works. Fantastic. So the first part of Velcro works when you scale it up. Now, the genius of Velcro is that you can unstick it easily, right? So let's try and unstick it easily. Why don't, yeah, you try and tear that way. Oh, that's not really working, though. She's had to pull it, and it's still there. Oh. OK. OK, guys, put this in the middle. If you just put that down there in the middle, yeah. Fantastic. OK. Thanks very much, guys, for trying out the gel Velcro. Thanks very much, yeah. OK, so look. The unsticking doesn't work very well when you scale it up. Did you notice that? They had to actually use their hands, which would be difficult if you were doing it with your own little unstrapping your shoes. And why is that? Well, we've scaled it up exactly. So we've got scaled up all the material dimensions. And actually, when you scale up nylon, which is what it's made from, this is what you get, this stuff. And it's actually not very flexy. It's quite stiff at this scale. And so the genius of Velcro is that when you're unsticking something, the little heads, these things here, they flick back really easily. If you have a look, you'll see they flick back really easily. And that noise it makes, that scratching noise, I'm making it now, like that. That's these little rods vibrating after they flicked, right? So that's where the sound comes from. In fact, did you know that the military have silent Velcro? Yes. Interesting, isn't it? I mean, you can sort of expect that. But so look, the thing is that you can't just scale things up and expect them to work, because the physics changes. And the physics we're relying on here was elasticity. And actually, by scaling up the dimensions, that didn't really do us any good. So sticking works, but unsticking doesn't work. Let's think about delving even deeper into this microstructure and looking at different forces down there and seeing what else we can manage to do. And I've got something here that really is marvelous. And it's at a much smaller scale than Velcro. And it's on this little tiny silicon chip here. And it's a machine. It's called it's a little MEMS machine, microelectronic device. And it's smaller than the width of a human hair. So even though I'm showing you this little device here, but there's no way you can see it. We need a really strong microscope to see what I'm talking about. And it just so happens we've got one. We've got an electron microscope outside, which uses electrons to see instead of light. And it can see incredibly tiny things. Fantastic. This is great. So this is an electron microscope. This is John.
Hi, Mark.
Hello. And this is Kelly, who's doing the tilt. And we've got one of these machines inside this microscope. It's in there. So it's on a sample holder, and it's deep in this machine. And this is the visual output from the machine. So John, what we've got here is I'm right, just to get the scale, isn't it?
Yeah, we've got one of your machines. We've planted it in this field of Velcro to give you some idea of the scale. So you can see the Velcro hooks here. As we take the mag up, you can see we put another scale.
So this is Velcro, and we're zooming in to see the machine behind it. And what else is behind it?
Ah, well, that's a head louse.
A head louse?
Yes.
So that's what a knit, is it?
A knit, if you want, yes, if you must.
They were the bane of my childhood. I used to fall out of my head. So can I see it face to face? I've never actually seen one face to face. It looks like a weird kind of cactus. Look at that.
So if you look here, human hair would occupy this sort of space.
Right. So this thing's about the width of a human hair.
Yeah, it's about twice the total width of a human hair.
Amazing.
Because it has to grip.
Yes.
So it puts its legs around and grips the human hair.
It looks like these weird hairs all over it. And behind it is the machine we're talking about, isn't it?
Indeed.
This type of micromechanical machine. Wow. These look at those holes. So these are all moving parts, aren't they?
They are indeed.
Yeah, so all these, this is a machine that moves, and its features are 1,000th of a human hair width.
Yeah.
Around?
These
Yes.
holes are about 5 microns. So.
Absolutely amazing to be able to make machines at this scale, don't you think? Smaller than the hair on a kind of head lice. That's incredible. So but why would we want to make machines this small? So you're all used to smartphones and tablet computers that do cool things, like they change the screen to suit which way up you're holding it, right? So they basically know which way up is. Now that's really cool because this is an electronic machine, but it knows which way gravity is pointing. Now, how can you do that if you're an electronic machine? Well, the basic principle is this. You have some sort of rod and a mass. And if it's in this orientation, you know which way gravity is because it's down. If you turn it, the rod bends because of the mass. And so now you know that down is that way because it's deflecting that way. So what these things do is that if you measure that deflection, you can know which way down is. So you do that, it goes that way, and you do that, it goes this way. So essentially these, what is called accelerometers, they measure forces, and they measure the direction of the forces acting on it. And in the case of gravity, that's very useful to know which way an image is up. So I want to show you what the accelerometers in these types of machine look like under the microscope. Okay, you can see it's made out of silicon, and the great thing about making it out of silicon is it's integrated into a silicon chip, so it works at a scale where electrostatic forces are dominant. But a change in the electrostatic forces, because these two things are nested together, so that if they separate slightly because they've changed in orientation, because you've turned it, the small amount of electrostatic charge that changes is very easy to monitor. So it's not just that it can do cool things for you, it can save your life too. Wow. Okay, fantastic, a little car. So, what's this got to do with it? Well, this was my first ever car. Well, it wasn't really, but anyway, I wish it was. I wish I had been that kid. Okay, now in the front of all cars, every car that's made now, and in the front of this car, which has been retrofitted, is one of those accelerometers. And it's measuring forces, right, by weights moving around and the electrostatic forces in it. And that gives a readout, a little electronic readout that goes into this silicon chip here. So there's a computer in your car, and it reads out the forces from the accelerometer. So this car knows what forces are acting on it. So I'll show you, we've got a readout of the accelerometer. If I hit it there, you can see a little force is registered on there, all right? You're wondering what that red line is. We've set that red line as the maximum force this car would like to have on it before it thinks it's in a crash. So below that, there we go, a little one like that, and it's not going to deploy any safety measures. If it hits a big force, it thinks we're in a crash, I better deploy some safety measures to save my passengers. Fantastic. Shall we try it out? Now, I think what we want to do is sort of set this car on a kind of collision course with a wall, maybe there. Are you guys okay with that? Are you? You want to stay there? Can I ask you guys to move out over here? Is that all right, just for the moment? And you'll get a better view of the crash, honestly. Right, fantastic. We've got our crash site already prepared. Well, it wouldn't be a real crash unless we had a passenger, would it? Are there any volunteers? Yes! Okay, good. A good volunteer, fantastic. Let's have a round of applause. Okay. Crash test dummy. Clunk, click, every trick. You don't hear that these days, do you? All right. It's now... Oh, I've got that wrong. Okay, let's put over the shoulder. Right. How are you feeling? What's your name? Should have asked you that earlier, shouldn't I? Crash test dummy. I don't think you're a dummy. Okay. Fantastic. Crash test dummies in place. Okay, here's the arming button. This is so James Bond. Arming the safety measures. Okay, it's armed. You want to do a countdown? 5, 4, 3, 2, 1. How are you feeling? Okay? A bit shocked? I know. Fantastic. Oh, yes. Right, off we go. Anytime you see something really amazing happen, really think, at what scale is that thing happening? And it's almost the